In this video, we will look at the relationship between the fusion rate of a gas and the temperature. So once again, we will be using K equals 1/2 mv squared once again, and K is T, m is molar mass, and V is the fusion rate R. So refer to the previous video if you want a clearer understanding of how I use the formula for kinetic energy to derive Graham's law, which was in the previous video. So in this case, we assume that the molar mass will be constant. So let's write two equations now. Well, actually, before we do that, let's move things around to make it so that the m, our constant, is on one side. So let's move the variables to one side and keep the constants on the other. So let's just multiply both sides by 2 and divide both sides by r squared. And we get that 2t over r squared is equal to the molar mass. And let me just write this so that it is more clear. And this is the thing, and we just rearranged it to make that. And in the last video, I know that I kept the k as a k, but it didn't matter in the end since the k just disappeared. But in this case, we have to change the k to a t because we have to relate t and r. So let's just say we have two gases once again, gas A and gas B. Gas A has a temperature of TA and an effusion rate of RA. And the other side we will have 2TB over RB squared. Let me put a parenthesis around that. And this will be equal to the molar mass. And notice how we are keeping the molar mass constant. In other words, we are not changing the type of gas we have. So now let's do some algebraic manipulation in order to get what we want. So 2TA over, I think it's RA squared is equal to 2TB over RB squared. And this is because we can substitute the molar mass into here, and since this is equal to this, then we can shove this into here. And looking at this, we can rearrange this to make it fit. So what I would do is I would multiply both sides by a fraction in order to cancel things out and move the variables to one side and to the other. So I want the t's on one side, so I would divide both sides by 2tb, and I would multiply both sides by ra squared, and you'll see what happens very soon. So on the left-hand side, if we multiply this by this, the 2's will cancel out, and the ra squareds will cancel out, leaving ta over tb. Now, what happens on the right-hand side? Well, our 2's will cancel out once again, and I think this time our TB's will cancel out, so we're left with RA squared over RB squared, and this is the relationship between TA, RA, and TB and RB. Now we can go even further to say that the square root of TA over TB is equal to RA over RB. Now I know all this is just intense algebra, but trust me, if you ever take a physics class, learning how to algebraically manipulate equations will be very, very helpful. So this right here is our final equation that compares the temperatures and the effusion rates. So as you can see, if you increase the temperature, then the effusion rates will increase as well for the same gas. And also note that we can use maybe velocity instead of the effusion rate for our questions, since they both mean essentially the same thing. So let's take a look at an example question. So let's just say we have a certain gas. I'll make one up. Let's say we have some oxygen gas, and it effuses through a pinhole at a rate of 5 moles per second, and let me put 5.00 to do some sig figs. 5.00 moles per second at 50 degrees Celsius. And let's just say if we increase the temperature to 100 degrees Celsius, what would be the new effusion rate? Well, let's use our equations, and let's make sure to do everything in Kelvin, since you never want to plug in anything that has to do with Celsius, since that can lead to wrong answers in chemistry. So this is 50 plus 273.15. We get 323 Kelvin, and we get 373 Kelvin. So now we can use the equation that we got from our calculations. So the square root of TA over TB. So we know that TA is 323 Kelvin, and TB, which is the condition after, is 373 Kelvin. And this is equal to the fusion rate for the first situation, which is labeled as A, and that's 5 moles per second, so 5.00 moles per second, over the new effusion rate, RB. And note that this situation over here is situation A, and situation B is over here with an unknown effusion rate known as RB. So doing the math, I get that the effusion rate for the scenario in case B, when you increase the temperature to 100, is going to be 5.37 moles per second, and that's our answer. So notice how increasing the temperature increases the effusion rate, or the velocity of the particles. Now let's look at the Maxwell-Boltzmann distribution, showing the relative amount of gases at certain speeds with varying temperatures, such as 100 Kelvin, 1200 Kelvin, and even 3000 Kelvin. So at higher temperatures, there are a wider variety of speeds gases can go, so the gases can spread out over these speeds, and that's why the relative abundances are quite low and kind of spread out, and that's why we have a very low hill. And also note that the average velocity, or you can think of it as where the peak is pretty high and toward the right. Now let's look at low temperatures. For low temperatures, most molecules can only move in a small range of speeds, which is why you have a high curve, since most of them can only be in this certain range, and thus they are highly abundant in this low range of speeds. Now the average is much lower as well. So this looks identical to the Maxwell-Boltzmann distribution when we altered the molar masses. So when at low temperatures, we have a peak that's high and toward the left, and as you increase the temperature, the curve kind of settles down and it moves toward the right. That's all for this video, and have a nice day.